years, 9 months, and 2 days, and it's done it 2,773 times, it doesn't tell you a whole lot because 2,700 of those could have been the first week the router was brought up, 3 years ago. But on the other hand, if the router rebooted 7 days ago and you've got that many, then you can be relatively certain that the health of this router is, or the network is not very stable. So it's relative. And the output down here for whether or not you've got authentication, how many LSAs have actually been generated in area 1. Again, take a look at use that in reference to gauging the health of the router. Show IP OSPF database, again, the process ID. And this particular router exists in area 1, 0, and it also exists in area 1. So this particular router is an area border router, just by being able to take a look at that. And show IP OSPF neighbor tells you the relationship that you have with those neighbors, whether or not they are, you've got a full adjacency created, or whether the neighbor is a designated router or a non-designated router, or whether you have a point-to-point connection across the serial interface where you've got a full adjacency. So knowing what kind of adjacency I should have, you'll be able to determine if what you see there is correct or incorrect. And show IP OSPF neighbor, show IP OSPF neighbor detail. How long has the neighbor been up, how many link state changes you have, and so on. So the same output, almost identical, you would expect to see on a router in a classic environment as same as you see here. So pretty quickly that we went through module number 8, but now all we have left remaining for the lecture for the day is module number 7. So that's really why I wanted to kind of go out of order a little bit. I know that some of you guys are likely following along in your student material, so I apologize for you having to skip and go forward. Now you got to backtrack a little bit. So this is going to be module 7. So I'll give you a second to get your student materials in line with what I'm lecturing on. But I wanted to make sure that we ended today on material that you have a lab exercise associated to, so that you can do the labs accordingly. All right. So SD-WAN features, module number 7. Quite a few features we're going to talk about in here. So we start off with NAT, network address translation. And there'll be some uniqueness involving NAT here for SD-WAN, but the concepts of NAT still apply. In addition to NAT, we've also got CFlow-D, and CFlow-D is somewhat analogous to NetFlow on your C-Edge router. So CFlow-D and NetFlow go hand in hand. We'll talk about that as a feature. In addition, there's also going to be the lecture on the material that your lab is going to support, which is TLOC extensions. And then we'll follow that up with QoS. So those are the 4 primary, I'm sorry, there's one more after your CFlow-D, and that's setting up zone-based firewalls. So again, you guys individually, some of you guys might be using all of these features, and some of you guys some of the features, and maybe there's some of you that won't be using any of these features, but they're all included in lecture in this module, with only one lab for TLOC extensions, however. So like I said, first feature is going to be SD-WAN NAT, network address translation. So you've got documentation available here. Now this is just from the student materials. That's actually incorrect, because there's no more anything.viptilla.com. So if I were to click on that, it's probably going to fail. And if it doesn't, it means I remapped it to the SD-WAN-docs website, which is really where you would take a look at that. And so as you can certainly see, that's where it takes you to. So I'm going to copy that, and I'll send this to you guys in your chat window. So again, put this in your favorite so you know that you have it. So these are your firewall ports. So if you're setting up connectivity between your controllers, as well for your DTLS connections, or between your WAN edge routers and your controllers, also using DTLS, make sure that if you've got firewalls in place that you're fully aware of the port numbers that need to be opened up and whether or not you're using TCP for your control plane or using UDP. In other words, DTLS or TLS. So because if these ports are being blocked, not opened up by the firewall, a DTLS connection is not going to be created. So if this guy here now, if vManage can't get to vSmart across a DTLS connection, he knows that there should be a vSmart there, no changes are going to be allowed until he is reachable. So a firewall that might be blocking your traffic is really not going to be a good indication. Now, we got four different versions of NAT. We got full cone NAT, symmetric NAT, and then on the next page we talk about restricted cone NAT and port restricted cone NAT. So let me quickly just explain these slides. I know that most, if not all of you guys already know what NAT's all about, right? Network address translation. So here we have host A that is sourcing traffic on port 2001. We're going through a NAT device that's going to map host A to host Z. In other words, this might be a private to a public address, and 2001 gets NATed to 3001. So this is what's going to be visible on the outside, right? So based upon our NAT filter, though, our NAT filter says any address, any port number. That'd be the example of full cone NAT. Well, if you've got full cone NAT implemented, this goes out on to destination host B and port 90. And if you use anything and anything, that means that I'm going to allow traffic inbound on any address on any port number. That is a recipe, in my opinion, for disaster. But anyway, that is because if you really wanted to only communicate to host B, you would never use full cone NAT. On the other hand, another choice could be same mapping. So we're still, the source is host Z, port 3001 because of the mapping. And on the initial packet, destination host B, port 90 is where the traffic is destined. Our mapping says the host is host B, but only on port 90. So if I communicate to you on port 90, then traffic even coming back to me from the same host on port 91 would be blocked. And because these guys are not host B, then their traffic is blocked as well. So that would be from or to the host on the port number and back from that host on the same port number. That's symmetric NAT. Now, restricted cone NAT, again, same mappings as before. The source is going to be host Z, port 3001, and we're going to destination B on port 90 as before. So our NAT filter is still host B, so certainly host C is going to be blocked, and any port number. So the traffic goes out on port 90, so because the filter says any port number, traffic coming back from host B on port 91 would be allowed. And then finally, we have at the end, again, same mappings here. So source is Z to 3001. We're going to host B on port 90 again, but our filter says any host as long as it's port 90. So traffic goes out on port 90, and even traffic coming back on port 91 from the same host would be blocked, but traffic coming inbound on any host would be allowed as long as it is port 90. So those are four different examples of what NAT's all about. And I think I might have put this in the material in the slide deck. Oops, looks like that's broken now. I can't find it. So that's just basically a RFC that I downloaded or made reference to out on the internet. It's an IETF document. But I think we just do a search on restricted cone NAT, for example, or symmetric NAT, and that'll be the same link here. For some reason, the link is broken now. It worked at one time, but it doesn't now. This kind of gives you, if it's useful to you at all, it gives you examples of which types of NAT traversal combinations is mostly encountered out there. So public to public, full cone to full cone are more common, and full cone NAT to symmetric NAT. But what's also common out there is symmetric NAT. But if that's being used, what the red means is there's not a direct IPsec tunnel between a pair of hosts, but rather you're going through a hub. So those are typical implementations that you see for NAT. Now we can now configure NAT on our routers, and that is as of version 18.3 or higher. So this is relatively a new feature, but you got to have a relatively current version of software to support this. Now, if you do a show control local properties WAN interface list, all you're looking at for NAT is just this one entry right here. It'll tell you the NAT type, and an E indicates endpoint independent mapping. That's your NAT type. Now, to configure NAT, normally this would be done from a feature template in vManage, but if you were going to do this via the CLI, or you want to look at this as a result of that feature template, there's going to be 3 commands that need to be configured on your C-edge router. So this is specifically an example on your C-edges. So 2 of those commands are the same regardless whether you configure NAT either globally or you implement NAT through a data policy. So number 1, you go to the interface. This would be on your SD-WAN side, because remember, here's your router. SD-WAN is in this direction. Back here, the translation is going to be, this has to be the inside, and that's going to have to be the outside, right? So all we've got to do is configure which interface is on the outside, and then we configure that magical command to make NAT work. So the command to actually configure NAT is the same as it's always been. IPNAT inside source is your command. That's how you configure NAT. Then what type of NAT is it you want to configure? In this case, we're defining an access list. And so what this parameter is going to define for us is what addresses are we going to allow to be translated. And most of you probably know this already. And then this parameter here says what we're going to translate those addresses to. This is what we're going to translate them to. And in this case, we specify interface gigabit 01, for example. So any address that satisfies that access list gets translated to the same IP address that we have configured on gigabit, whatever the number is, and the overload keyword, you probably know what that means already. That means PAT, right? Port address translation. So this is many to one. So since we're using PAT, what the address is that we're going to translate to is going to be the same address, regardless of how many users are satisfied by this access list. But each translation would be referenced by a different port number because of the overload keyword. In addition, now we can also have the third configuration globally, which is your IPNAT route, VRF with again, a default route with a global keyword. So this is global, or it can be configured by way of a data policy. And again, all this here is you've got a show policy from vSmart. Now this data policy, again, is not configured in the router, but rather in vManage by way of a policy pushed out to vSmart that in turn distributes it to the respective routers. So the direction is all. It's referencing a VPN list called VPN1. Don't really know what VPN1 is. It's not on the diagram. But sequence 100 is we're matching on this source address. In other words, anybody in subnet 24, 10.20.24, is going to be mapped to 10.0.12.12. So that indicates with the 32-bit mask that this is going to actually be PAT. And action accept, use VPN 0 to take it out to my transport VPN. Well, you've got some show commands for NAT. Again, I'm not going to read those to you, but certainly make use of those in your C-edge routers, and you can also take a look at your translations as well on your V-edges as well. So and use those commands if you get the opportunity. If you can log into your production network during the class and use these commands in your production network, it just makes the class, you get more value added contributions from the class by using these in your network. Because again, all of our routers are vEdge routers at this point. You can also look at this output instead from vManage's perspective. Remember the device options? So we go to monitor, network, the router we're going to monitor from, and we choose real time on the left-hand side, and then we choose device options, IPNAT translations or IPNAT statistics. And again, now you see the output more in a tabular format than you did via the CLI. But again, you still see that you've got translations taking place. And as a result of configuring that template we saw earlier, this would be the result of what you would see on the router. And if this is successful, if this is correct, and the only way you're going to know that is to scrutinize every line one at a time. So this is showing you that, hey, we've got IPNAT outside configured here. And that's on interface gigabit 1. Here's your IPNAT inside source command. So those two commands are as a result of having configured this via the device template. Okay, so that's NAT in a nutshell. If you're gonna use NAT on your routers, then so be it. I've had quite a few customers that are using their own security-based solutions. Maybe you're heavily invested already in Palo Alto, for example, and maybe you're using NAT, firewall, VPN functionality on Palo Alto. And if that's the case, then you would not be setting up NAT on your branch vEdge routers, but Palo Alto instead. Or you may choose to use your branch vEdge routers. It becomes your choice. Next is CFlowD and NetFlow. So CFlowD, the current version is version 10. The current version of NetFlow, this is going to be on your vEdge routers. This will be on your cEdge routers. It is also version 10. And both of those are based upon an industry standard called IPFix. And IPFix is also at version 10 as well. So commonalities between the three of them. So if you're going to be configuring NetFlow on your cEdge routers, again, it can be done either globally or through a data policy. So this kind of shows us our global configuration. So it's just a result of us typing in the command within our policy of flow visibility within our global configuration. Otherwise, if you want to do this via a data policy, you configure this within vManage as far as your policy configuration is concerned. And we're looking specifically the data policy that's called accept CFlowD. That's the name of the policy. And the direction is all. It is some VPN defined by a VPN list called VPN1. Sequence 100 is matching on traffic originating from this subnet going to this destination IP. The action to be taken if the sequence number is satisfied is to count the traffic for service CFlowD and send it to the data or send it to the server that'll be defined as well. Not shown here. It'll be an additional commands. In other words, we've got a data flow collector out there we're sending traffic to. And that data flow collector could be Manage Engine, could be, I use SolarWinds pretty often in an example as well, or whatever your data flow collector would be in your production network. And within your cEdge routers, we can clear application forward, CFlowD, flow all, or clear the statistics. And again, it's just a clear SDWAN, and then your NetFlow parameters. And here's some show commands as well, just letting you see, do we have packet counts that are incrementing for the most part for traffic that is actually being sent out to a data flow collector. So you can take a look at your flow count and also your flow statistics as shown here. And use these in your production network. Get an idea of what's expected in your production network. For flexible NetFlow, for flow monitoring, again, I think this link here should work. Yeah. So I think I added this one to my slide deck just to show it to you. Let me copy it. I'll also send that to you guys in your chat window. So more information to be uh, to use. And the reason I put this in here is because I had a student several classes ago that says, can you show us the documentation of how to actually configure seed loading? And so that this will walk you through that exact process, what all the parameters actually mean. So, and little research more on your part, but still, it's giving you a link that you can use directly to show you how to set it up. And to monitor this behavior from within vManage, again, we're still going to the real-time parameters page. We're looking at a particular device, and under the device options, type in an F or flow, and then you'll get those types of parameters that you can choose from. And again, you can look at the output within vManage without even having to know the command line syntax if you were to enter it in from the CLI. Again, kind of your choice. Okay, that takes us now to TLOC extensions. This one could end up taking us a little bit more time, simply because there's a lab exercise that's going to coincide with this. So let me first kind of show you the diagram. So for right now, just pretend that doesn't exist, and let's pretend this doesn't exist either. So what we have right now, before we implement TLOC extensions, is we have a connection on a pair of WAN edge routers, and both of these, by the way, are in the same site. So we have an MPLS connection on this router going to the data center, we'll say, hypothetically, and we have a connection on this using LTE going to the data center. Or in our lab, this could be gold, and then this would be silver. But both of them ultimately end up in the data center. But each of the routers have only one connection with no network connectivity between them. So you've got devices back here that are sending their traffic to CEdge1. You've got users back here that might be sending their traffic to CEdge2. Well, it's not rocket science, right? If I lose my gold transport and that's the only connection I have to SD-WAN, then any users using that path, they're pretty much toast, right? Same thing here. If people are sending their traffic to CEdge2 to use the silver transport to get to the data center, and you lose that, then their traffic is toast. So, but I've only paid for one circuit on CEdge1, and I've paid for one circuit on VEdge2. So if I could take advantage of both the gold and the silver on both transports, on both routers rather, then I get more functionality and it doesn't cost me anymore. So that's the idea. That's the idea behind TLOC extensions. So now you add a network connection between your pair of routers. Now, this happens to be a layer 3 LAN. So with this being a layer 3 connection, what that means to you is the IP address that you configure on this interface is one subnet, and the IP address that you configure on this interface is a different subnet. So therefore, the only way that we can communicate between the two of those is to be routed. So there has to be some layer 3 functionality that routes between those two networks or those two subnets. So that's first and foremost. Now, with this being a layer 3 connection, this is CEdge only. This functionality is not yet available on vEdges. Now, I haven't looked at the release notes for 19.2 yet. I have not found out if TLOC extensions over a layer 3 network is supported on vEdges or not. But my last reading was this is only available on CEdges. Now, if this were a layer 2 connection, if it were a layer 2 connection, and this is 1.1 and this is 1.2, then that means that that would be supported both for CEdges as well as vEdges as well. So layer 2 TLOC extensions is supported for both types of routers. So this is what your configuration would be if you were implementing CEdge routers. This is not what it looks like if you configure TLOC extensions for vEdges. My lab exercise is using vEdge router. So I provided this for you that you can use as a guide if you're rolling out TLOC extensions in your production network using C edges. And I use the lab exercise if you're actually rolling out V edges. Now down the road, that might be swapped, but right now that's how it is. So if you've got TLOC extensions over a layer 3 connection, notice that what we're really setting up here is the tunnel mode of something called SD-WAN. So tunnel mode of SD-WAN is really a GRE tunnel, right? Now this is not part of SD-WAN. This is extending SD-WAN down here. So one of two things is going to be happening here. So by setting this TLOC extension up the way it's shown here, we may be only setting up TLOC extensions in one direction. So in other words, I want to be able to send traffic here, but redirect it over here to my MPLS connection and get me connectivity to my data center, for example. This being an LTE connection, I only want to use that as a last resort. But if I do lose connectivity in MPLS, I can still continue to use that. Now, if you want to be able to make this be used, like, for example, this is gold and this is silver instead, where you want to be able to use both of your transports, then you would have to have two interfaces across here. Two interfaces or one interface configured with two sub-interfaces, one or the other. And so that's how I have it structured in the lab. I've got this set up so that you've got one physical interface here, and this would be sub interface. And by the way, this is going to be gig Ethernet 0/3.100, and this would be gig Ethernet 0/3.200, or .1 and .2. Same thing here, gig Ethernet 0/3.100 and gig Ethernet 0/3.200. And then I would have an IP address reachable via this network and an IP address reachable here as well. Now, here's the goal. By having gold only configured on router 1 and silver only configured on router 2, it's going to act as a redundant path in both directions. So notice on this side, gigabit 02 here is this interface, and you configure the tunnel interface option. Now, when you configure the interface 1, this is the connection here, you're specifying a TLOC extension GRE2, the address on the other side, which would be here. That's the IP address of the extended interface. So we pointed in that direction. And likewise, on this side, we have a TLOC extension GRE from the address configured on this side, which is 10.1.1. So you see, the cross connect is only in one direction here. But if you wanted to be able to use gold and silver, you would replicate these commands on both sides. Because the way we have it structured in the lab, now you can follow these commands. These are the command syntaxes that you would use underneath SD-WAN to configure TLOC extensions on both C-Edge1 and on C-Edge2. Now, let's change this just so that it makes sense in our lab, gold and silver. So we're going to set up two sub-interfaces, one here and also one here, as an example. And we configure a tunnel interface that points in this direction. And we can, on one sub-interface, we configure a tunnel interface in the other sub-interface pointing in that direction. So now what happens is we've got redundancy for transports. So traffic that is destined to the gold transport, if traffic originates on this side going to C-Edge router 2, it goes across this extended tunnel interface over to C-Edge 1. C-Edge 1 has connectivity to gold. So users that are sending traffic here can actually get to their servers via the gold transport using this extended interface if something happens to the silver transport. Likewise, users that are sending traffic to the gold side, if we happen to lose the gold transport, we've got an extended tunnel interface here. So I can go across this interface now to the extended tunnel interface and hop out my silver transport and get to the same destination network. So that's what we're going to be doing in the lab. You're going to be setting up two tunnels, but pointing in opposite directions for redundancy's sake. So look at the advantage here. If I've got two sub interfaces configured with a tunnel interface in opposite directions, this router, if I log into this router and I do a, say, show control connections command, for example, show control connections, normally, and let's make this match more realistic to our lab. So this is silver and this is gold. Better yet, I think in the lab, this is actually MPLS in gold. So if I log into this router and that is show control connections, I should be able to see my vManage, vSmart, vBond controllers via both MPLS as well as across the extended connection across Gold. Now, if I can see my vSmart controllers here via the Gold transport, and all I have is physical connectivity to MPLS, the only way that could possibly happen is across this TLOC extension. Likewise, if you log into this router and do a show control connections, if I can see my vSmart, vBond, and vManage controllers via MPLS, then the only way that could happen is across the tunnel interface through the extension provided to me from CEdge2. So that'll prove to you that even though you've got one physical connection to a transport, you can take advantage of the transport of the other router locally. And still, all of your policies still take effect. All of your requirements for monitoring the health of the transport take effect. So you might say, hey, all of my traffic here is using gold as my transport because maybe you've got higher bandwidth capacity there. And a BFD starts saying, hey, your bandwidth now is out of profile, or your packet loss, or your latency, or jitter is out of profile. I can still take advantage of the TLOC extension and send my traffic now across my TLOC extension to the other transport, even though I'm not physically connected to it. So this is why TLOC extensions become a really popular tool. Is if you're using application-aware routing, it also works with that. But you may have an option, not part of this lecture, but you may also have another option. What if you've got traffic that originates between these pair of routers and you've got, let's say you got a switch back here and you got all these users back here that are VLAN, right? VLAN 1, 10, 20, 30, 40, and so on. And this is connecting to both this router and also this router. Again, this is kind of the connection you have in place. So you've got gold and you have MPLS. Now, if your goal is, I just want to implement redundancy. Well, TLOC extensions obviously gives you redundancy, right? I can send traffic in this direction and take advantage of my MPLS fabric. I can send traffic in that direction and take advantage of my gold transport. But in addition, TLOC extension also lets you take advantage of BFD, so I can monitor the health of the transport. And if that falls out of profile, then use the other transport. So that's the advantage for using TLOC extensions. But if you only want to set up redundancy, you don't have to use TLOC extensions for that. What you could do instead is set up VRRP, right? Set these guys up. This is my active forwarder, and this is my standby forwarder. So this becomes my active path only to the data center. The only time I'm going to use this would be if I lose connectivity, because with VRRP and HSRP, which is not supported here, you can monitor or track an object, such as whether an interface is up or down. So if this interface here happens to go down, I can decrement the priority of this router. Let's say right now it's at 100, and let's say this is at 90. I can decrement the priority of this by 20 to make it 80. Now 90 becomes higher, so this guy goes active, and then this guy goes standby. Now, we use this guy to forward traffic, so MPLS becomes my transport. So you see, I can use VRRP and not even worry about TLOC extensions, but you don't get the benefit of TLOC extensions beyond that of just default gateway redundancy, which is really what VRRP gives you. So, but I can't really come up with a given reason, a valid reason anyway, why you would use TLOC extensions and VRRP. So typically, if you want to take advantage of router redundancy and or transport redundancy rather, and the ability to select load, based upon your discoveries of BFD, then TLOC extensions is going to be your best decision. So anyway, that is TLOC extensions, and I want to go through that discussion one more time before I turn you guys loose to lab and show you what the configuration in the routers, what it would look like.
What are some use cases you normally see that implemented? Do you find most of your customers using dual edge routers at their endpoint sites, or does it just depend on the size of business, or?
Well, it depends upon the critical nature of that particular branch location, right?
I gotcha.
Yeah, so if you've got a branch location that is, you've got to have connectivity to the data center, and you don't want, anytime you have best practices, you never have a single point of failure, right? I mean, that's just not part of best practices in anybody's book. So either you would have a single router that has connectivity to two transports. Now you've got at least transport redundancy, but you still have a single router there that gives you a single point of failure. So another solution could be that you've got, again, I'll set this as silver instead of LTE, but you might have two transports. This guy's connecting MPLS and he's connecting to here. This guy connects to here and also connects to there as well. That would be best practices. And if that's what you use, then you don't need TLOC extensions because you already have router redundancy and this would not be there. And you've also got transport redundancy as well. But when you are trying to maybe conserve money, I only want to buy and pay for two circuits instead of four circuits, this will be a more cost-effective solution for you. So
Okay.
that's your use case right there, right?
Okay.
And the other example would be, hey, I do have a pair of routers there, and I want all of my traffic to use MPLS and only use this LTE if I lose MPLS. That's another example of TLOC extensions in this diagram.
Okay.
That anybody else come up with any scenarios that you can think of where TLOC extensions would apply? Ultimately, you're taking advantage of a total of 4 transports when you're only buying for 2, only paying for 2. Because I'm using this transport from this router's perspective by going across the TLOC extension to get there. Only reason I would do that is I got an outage here. And likewise, if I'm using this router for connectivity and it goes down, I can use my TLOC extension and still get where I need to go to using the transport of my neighbor router.
Gotcha.
These would be configured for the same site ID.
Okay. Yeah, I was just thinking from the standpoint of only having one edge device, because you can still use TLOC extensions with just one edge device, right? But it doesn't give you that default gateway redundancy.
No, TLOC extensions is always between a pair of routers.
Or excuse me, I'm thinking of never mind. I'm thinking of just using what we were learning in the policies with failing over one to another and what so forth.
Yeah, that would be that's application aware routing, where this router may have connectivity like it does in our lab. He's got connectivity to the gold, and he's also got connectivity to silver.
Yeah.
So,
okay.
So, Roger,
what's that?
How would the routing internally look like? So, how would you determine the load on each of the edges, of the C edges?
So the first thing is the use case here. How are you implementing TLOC extensions are you using, or one, you've got a primary transport and you've got a transport of last resort, or
No,
do
we're,
you
we're,
have
we're
like
thinking of having like two internet connections, right?
okay,
And just have an active uh,
so
scenario.
internet one and internet two,
Correct.
okay? So, and that you only have one transport configured on each a pair of routers, is that what you have?
Well, we don't have anything yet configured, so that's what I'm trying to figure out what to configure. And I'm guessing it'll be one transport with
Well,
the
if you
two.
have, no, if you've got a router at a branch location and you have two transports, it makes sense to just do this, right?
Right.
And then later on, if you make the decision, well, I've got transport redundancy, but I don't have router redundancy, then you could add your second router, get rid of this connection, put it here, and then you can use TLOC extensions.
Right, but on the LAN side, how does that change?
Um,
Because if I have one router, all the traffic's pointing to that router, correct?
Yeah, but this router can make the decision of which transport it wants to use for what traffic. If you're saying you're using application aware routing, for example, because you could pin some traffic to this transport of gold, other traffic to that transport of silver. Or if you didn't do application aware routing, it would just load share across both transports by default.
Correct.
If that's adequate for you, if it's applicable to the applications at hand, then that's plug and play. That's what you get automatically.
Right, and my question is when you have the two routers.
Okay, so yeah, I'm trying to make you be as specific as you can because this is one example where
Correct.
each router is connecting to two transports, but one transport is never used unless you lose this guy completely. That's this example in the book. But if you change this to where this is a gold transport or internet one, and this is internet two, we'll call it silver. Now, do you want to be able to use both transport? You still can. So traffic, you could say some traffic is destined here that is going to use the silver transport. Other traffic is still coming here using the gold transport.
Okay, and that would be determined by a routing protocol.
That would be determined by application aware routing, right?
Okay. Okay.
Based upon your pinning an application to a given transport. Because another reason that you're doing this is you might say, even, I've got all traffic or some traffic going to transport gold, other traffic going to transport silver. And transport gold right now is set up in a full mesh. And you want some other kind of traffic, whatever it's going to be, to still use the gold transport, but rather just hub and spoke. That's all going to be controlled by policies. That's got nothing to do with TLOC extensions. TLOC extensions is merely saying, I've got this transport that I want to use, but I can't get to it. Now I've got another path that I can use to accomplish the same goal. That's what TLOC extensions are going to do for you.
Okay.
At the same time, you only have one transport here, you only have one transport there, and you've got a network connection between the two of them. That is where TLOC extensions is intended to be used. If you have a pair of routers and you have two transports, each connecting to two transports, there's no reason, no use case for TLOC extensions because you already have router redundancy and you've already got transport redundancy. There's no
Right.
need, there's no use case for TLOC extensions there.
Right, and you can reach both transports through one single router, right?
Exactly, correct.
Okay.
This may be a stupid or ignorant question, but just for my knowledge, do you
Okay.
configure CEdge 1 with the same um, internal LAN interface as CEdge 2, or that would be an IP conflict, right? So are you configuring it with two different?
Oh, no, this interface here, see these two interfaces, they could be routers that are sitting right on top of each other. And this would be address .1 and that'd be address of .2, right? But the
And then
same,
you just point some of your workstations to .2 and some of your workstations to .1, or how would you?
sure, I mean,
I've just never seen that before. That's why I asked.
For that, or these could be connecting to a switch, and this could be VLAN out. And VLAN 1 goes to this guy, and VLAN 2 traffic goes to this guy. You could do it that way, right?
I gotcha. Okay.
Because back here, you might be using either VRRP or even HSRP to control which C-edge router gets your traffic. Or you could just configure VRRP locally on those and handle and do the same exact thing.
Interesting.
So you could probably come up with about 40 or 50 different scenarios of where TLOC extensions could be used. But ultimately, you have a pair of routers that are co-located, and each router has a single transport or single connection to a transport. But you want transport redundancy. That is the end goal of TLOC extensions. We're extending the SD-WAN by using an extension to our transports between a pair of routers. That's what TLOC extensions is for. Whether it's layer 2 between them or layer 3. That's
So the
TLOC.
question I think this kind of brought on the question after hearing all these questions is, you still run an IGP between the routers, because this is the transport, it gives you availability between CS1 and 2. You still have to run OSPF so they know each other.
Here's something that does not run by default. So this guy here is going to have BFD connections to all kinds of routers out here, right? And this guy is going to have all kinds of BFD connections to routers out there. But from router to router across a TLOC extension, there is no BF. So in other words, there will not be an IPsec tunnel created across a TLOC extension. Now, that's the default behavior. If you do want to run, like you just said, an IGP process, maybe you want to run OSPF between the two of those, then you would have to enable BFD, which is disabled by default on a TLOC extension. And then let OSPF, let the dynamic routing protocol be your guide of which transport's going to be used. But by default, there is no BFD on TLOC extension. So TLOC extension, as you can certainly see, just from the crust of the discussions we've had in the last 10 minutes or so, TLOC extensions is a very cost-effective tool that you can take advantage of. Have one circuit on each of a pair of routers, and take advantage of the total of 4 transports when you're really only paying for 2. Now, another reason to do something like that is, what if you happen to have a pair of routers here? Let's just say that these guys are co-located together, and this happens to be a vEdge 1000, and this happens to be a vEdge 100. This guy has cellular capabilities, but this router does not. And the only time you want vEdge 100 to ever be used is if you've lost your MPLS fabric here. So you're paying for one transport, and you only want to use this transport and pay for its use if you lose this guy. So that's another example of why you would use TLOC extensions. And another would be, maybe this is a vEdge 100 again, and you don't have enough interfaces on this guy to give you connectivity to all of your transports, plus have one on the local side. You do have enough for connectivity to one transport and one on this side. You're limited to the number of physical interfaces you have. By using TLOC extensions, I can take advantage of those transports locally on this router. So again, it could be as a result of the physical hardware that you happen to be using may be limited in how many interfaces you can configure. So again, the use cases keep on going and going and going, and you can probably come up with several on your own. But whatever that use case happens to be, you've got a pair of co-located routers that each are connected to different transports, but you want to take advantage of both transports on both routers. So whatever use case you come up with there, that's what TLOC extensions are used for. Now, I do want to throw one more, since we're talking about it, I want to throw one more, I guess, scenario at you here. Right now, what we've been talking about all along for TLOC extensions is a pair of WAN edge routers, and they're both in site 10, hypothetically, right? You got co-located routers. Well, this is also something that you could do with TLOC extensions. This router could be at site 10. This router could be at site 20. And as long as you've got layer 3 reachability between these guys, TLOC extensions is also supported there as well. So if you had a pair of routers that are geographically relatively close together, maybe you've got a router in Dallas and another router in Fort Worth. You could still use TLOC extensions between two different sites also, as long as you've got layer 3 reachability between those. You're probably never going to have layer 2 reachability unless you've got a switch here, right? But I suppose that's possible too. But TLOC extensions also works across site ID boundaries. And the way I know that is because that's what you're going to do in the lab. This router here is vEdge 1. This router here is vEdge 2. He is site ID 20. This guy is site ID 10. And TLOC extensions works perfectly fine between them. So kind of think about that. You have a pair, you've got a single router in Dallas, a single router in Fort Worth, two different site IDs. As long as you've got layer 3 functionality between them, you can use TLOC extension between them as well. And that comes with that introduces a whole new additional set of scenarios of why something like that might be used. But it is functional. You guys okay with the discussion for TLOC extensions? It's a pretty dang.
There was winter in my heart, and I was looking for the door to summer. I see a door, it leads
if you implement firewall functionality on your
There was winter in my heart, and I was looking for the door to summer.
I see a door, it leads to the place of my dream. Never felt so right, mystery is there to find. I know it belongs to me. My destiny calls to try. Open the secret in time while the moon's shining high in the sky. Better believe it's now or never. Open wide, step inside. Wonders behind the surface, shimmering light is so bright, so bright. I got a key, rustic and cold in my hand. I'll use it now. Fire burns within my heart. Somehow I know it belongs to me. My destiny calls to try. Open the secret in time before it's too late. Don't ask why. Better believe it's now or never. Open wide, step inside. Wonders behind the surface, shimmering light, so bright, so bright. Better believe it's now or never. Open wide, step inside. Wonders behind the surface, shimmering light, so bright. Better believe it's now or never. Open wide, step inside. Wonders behind the surface, shimmering
So the next step would be come up with your pairs. So zone pair, we're going to call the first zone pair configured that yet. That's going to come up on the next page.
There was winter in my heart, and I was looking for the door to summer.
I see a door, it leads to the place of my dream. Never felt so right. Mystery is the yet to find. I know it belongs to me. My destiny calls to try. Open the secret in time while the moon's shining high in the sky. Better believe it's now or never. Open wide, step inside. Wonders behind the surface. Shimmering light is so bright, so bright. I got a key, rustic and cold in my hand. I'll use it now. Fire burns within my heart. Somehow I know it belongs to me. My destiny calls to try. Open the secret in time before it's too late. Don't ask why. Better believe it's now or never. Open wide, step inside. Wonders behind the surface. Shimmering light, so bright, so bright.
An example. So we create a data prefix list called test prefix 2, and that is your prefix. So it's really the data prefix itself that is of concern as opposed to the name. But it's kind of hard to find what you're looking for if you don't have a good naming convention for those as well, as you guys saw when you created your policies earlier. A new zone list. So we got zone 1, zone 2, zone 3, test zone. All of those have to be configured, and which VPN are mapped to those respective zones. That has to be a mapping that's been defined. And this just shows us one of those. Zone 0 maps to VPN 1 or VPN 1. And then finally, define your match and your action criteria. So this is going to be a zone-based policy that we're configuring right now. And define your match criteria, and then subsequently the actions to be taken. You've seen all of this already in your policies lab previously. So you can just make sure that when you're choosing this, and you select the right information here, whether it's a source and or destination. And don't forget to also take a look at your default action. If you don't click on the default action and make a change, just remember the default is always going to be denied. And then you configure the application. So here's test zone 1 going to the destination of test zone 1. So this gives us the ability to set up a policy within the same zone, which is really good because zone 1 consisted of a lot of different areas that involve VPN 1, if you saw the diagram previously. So that feature richness you get with C-edge routers that you don't get with V-edges. And then finally, once your policy is configured, you go to your templates, go to your device template, scroll down to the very bottom of your device template that you're going to be associating to any given number of routers, and underneath your security policy, drop it down and find your zone-based firewall policy that you're going to be attaching here. Update it, and now all routers would automatically have to abide by your policy that's part of this template. So this shows you your C-edge routers for your show and your debug types of commands. So there's debug zone types of commands, and also show SDWAN zone-based firewall types of commands as well. Now we're not using zone-based firewalls in the lab. So if you are implementing this in your production network, certainly use those commands to your advantage so you know what the output typically would look like in your own production networks. And QoS, the last little bit of the material is for quality of service. That's another one of my favorite classes to teach, which is quality of service. So certainly, I'm not going to be able to teach you what you need to know with regard to QoS in 10 pages, but at least I'll give you the highlights here. So with your V edges and your C edge routers, this is what you get by default. You get Class 1, Class 2, Class 3, and Class 4 categories of traffic automatically mapped Class 1 to Q1, Class 2 to Q2, Class 3 to Q3, Class 4 to Q4. So even though you've got Q0 through 7 options, all this offered to you by default is Qs 1, 2, 3, and 4. If you want to take advantage of 5, 6, and 7, you got to manually set that up. But what we don't know just yet is what is Class 1, what is Class 2. We got to define all of that. So you look at your match criteria. So you match whatever you're looking for is based upon whatever you're defining that's going to be satisfied or classified rather as Class 1 traffic, Class 2, Class 3, and Class 4. Now again, this is inherently created by vManage, but you need to define what really is meant by Class 1, 2, 3, and 4. And 5, 6, and 7 if you tend to want to use those as well. So again, as a result of Class 1, 2, 3, and 4, you've also got your policy map that you're going to give it by some name. In this case, the name of the policy map is map 1. Here's where Class C1 is defined, Class C2, Class C3, and Class C4. This is going to be your queuing strategy. Now, if you understand quality of service, then looking at those commands should tell you how queuing is implemented on this router, just by looking at the commands. Notice we have a bandwidth command for class of traffic 4, bandwidth command for class of traffic 3, and here, but we got a priority command there. Now, what I will tell you is all of your queues, these 3 queues are 6 of the 7 queues, if you happen to implement those. If you're using a bandwidth command within that queue, what that means is, and I'll put this here, that means that you are using weighted round robin queuing. That's what the bandwidth command does. Now, the percent, this is why it's weighted. I'm going to allow 20% of my bandwidth to be consumed when I dispatch traffic that's associated to Class C2, which we know is going to be Q2. Class C3 traffic maps to Q3. I'm going to dispatch 20% of my bandwidth when I dispatch packets from Q3, and Class C4 maps to Q4, so I'm going to dispatch traffic from Q4 using 20% of my bandwidth. Now, because these are round robin, dispatch packets from Q2, then Q3, then Q4, and guess what? Go back to Q2, go to Q2, Q3, Q4, go back to Q2 again. Weighted round robin. But see, these are kind of equal, 20%, 20%, 20%. They don't have to be. You could say 25% here and 15% here and 40% there if you wanted to. They don't have to be equal. That's why it's weighted round robin. But because of the configuration we have, this one says priority. So whatever is traffic is in classified as C1 traffic, going to Q1 has a strict priority associated to it. Now, because Q1, class C1 traffic destined to Q1 is strict priority class, and the remainder of these is weighted round robin, then your entire queuing strategy for class 1, 2, 3, and 4 would be low latency queuing. And low latency queuing by definition is nothing more than a priority queue plus weighted round robin. That is the definition of LLQ. Now, if by chance you were to change this and put a bandwidth command here instead of a priority command, now you just have another queue that is set up in a weighted round robin queuing strategy. Now you'd be dispatching packets from Q1, stop after 20%. Dispatch packets from Q2, stop after 20%. Go to Q3, stop, go to Q4, stop, and then go back to Q1 again. So all 4 queues would be weighted round robin. So if you happen to be sending traffic like voice over IP and you're putting that as class 1, which goes to Q1, you better not use the bandwidth command on Q1. Because if you have a weighted round robin strategy, kind of think about this. If I happen to have voice over IP traffic in, again, C1 traffic goes to Q1, I'm dispatching 20% of the bandwidth. So I've got voice over IP traffic in there, maybe combined with other types of applications. Dispatch packets from Q1. Okay, 20% is consumed, stop. Now go to Q2. But wait a minute, I still got voice I need to send. Too bad, wait your turn. Go dispatch packets from Q3. But wait a minute, I got voice over IP that needs to be sent in Q1. It's too bad, stop and wait for your turn. Dispatch packets from Q4. Okay, now stop. All right, now Q1, you can transmit some of your voice over IP stuff. So if you put voice over IP traffic in Q1, and Q1 is defined as part of your weighted round robin queuing strategy, what's going to be a problem doing that?
Intermittent audio.
You're going to have audio issues, guaranteed. To what degree? I don't know. It depends how much traffic really you have in the other queues. Because if I can only dispatch packets from Q1 when it's Q1's turn, I guarantee you're going to have some issues with jitter to some degree, guaranteed. So always put voice over IP traffic into a strict priority queue. And the strict priority queue, for the most part, that's given you is Q0. Now you can leave Q0 the way it is, and Q0 traffic is where all of the router originated traffic goes to. You know, your BFD packets and your update packets to and from the control plane. That's being put into Q0. You want that traffic to take precedence over anything else. So if you do have an LLQ strategy, dispatch packets from Q1. Okay, now stop. Go back to Q2 now. Now, if I happen to have more packets show up in Q1, stop the round robin, go back to Q1, dispatch packets from Q1, and then go back and continue round robin again. That's what LLQ does for you. So traffic in strict priority queues, that's why they're called priority, because they take precedence over any of the other queues that happen to be round robin. So anyway, enough discussion about queuing strategies. Now we can shape traffic, specify what you want your shaping to be, and you apply the policy that you've configured to an interface with a service policy command and an inbound. Usually, if it's queuing, it's going to be in an outbound fashion, and you're using that as your name that you're binding to gigabit 01. So that's quality of service in a nutshell. Now, one more thing that I might want to talk a moment about, I'm getting really late in the day here, is random detect. So random detection happens to be configured on really Q2 and Q3 we know what they're being mapped to. So random, this is called RED, by the way, or CB RED, class-based random early detection. It is a congestion avoidance mechanism. Without getting into a long drawn out discussion, what random early detection is for is, this is queue number 3. So you've got some kind of traffic that's destined to queue number 3. Here comes that traffic. It's going into the bucket. So as the packets are being dropped out onto the wire, the queue is going to start filling up with packets that are different categories of traffic. You determine different thresholds in this queue that's going to be a drop threshold for different categories of traffic. So if I've defined, for example, FTP traffic here, I don't know, Telnet traffic here, Citrix traffic here, and I specify, I don't know, web traffic here. The whole idea is when I reach a predetermined threshold, when the depth of this queue reaches that predetermined threshold, automatically and on purpose, start discarding a percentage of FTP flows. the queue continues to rise. When I get to another predetermined threshold, on purpose start discarding some percentage of telnet packets. The queue continues to rise. Once it gets to this level, purposely start discarding some percentage of Citrix-based traffic, and the queue continues to rise. And then when it gets to this level, then purposely start throwing away web type of traffic to a percentage. Now, the whole purpose behind random early detection is to try to prevent this queue from ever filling up completely. Because if that queue were to fill up completely, and let's say that it can handle 40 packets, if I've got 40 packets right now sitting in this queue, it doesn't matter what the next packet is or how important that next packet is. It's only got one place it can go, and that is into the proverbial bit bucket, and it gets thrown away. So the whole, and that's referred to as tail packet discard. And you'll see that abbreviated TPD sometimes, or the type of discard is called tail drop. So the whole purpose of random early detection is to set up thresholds within a queue that multiple categories of traffic are going to, and to prevent the queue from ever filling up completely. Because you want random early detected dropped packets. That means it's doing its job. On any queue where random early detection is configured, you want to see 0 tail drops. And if you do, but you see random early detection drops, that's good. Random early detection is doing its job. So that's QoS in a nutshell. So all of these strategies for QoS, though, it's going to be done by way of a localized policy. And again, you use this, basically it becomes a wizard for you, just like you did an application aware routing policy earlier. So you configure all of those steps. Here we're defining our classes mapped to the respective queues. And again, you can edit each one of those, or you can also add a new class map. Maybe you want to configure class of 5, class of 6, and class of 7, if you want to. So this now, once we've defined our interests, we configure our forwarding classes. So here's a QoS map name. Certainly click on next once the name's been created. And then you can start, again, filling in the rest of the information. Your access control list, your ACLs if need be, your route policies, and then finally your policy definitions. So once those have all been defined, in this case, we have our 5 queues there. So Q0 is our strict priority queue. Q1 through Q4 is weighted round robin. Notice that random early detection is only configured in queues 1, 2, and 3. It could also be 4 and 5 and 6 as well, but you only want tail drop configured on your strict priority queue. The only time you purposely want to throw away packets in the strict priority queue is if you have to. And the only time you're going to have to throw packets away is if the queue is full. And so here's your access control list. Again, by DSCP values, you can make that decision. But one very quick thing I want to mention that usually most people aren't truly aware of is how do DSCP values map to assuring forward values, AF values. So you guys have heard of things like an AF31 and an AF32 and an AF33 or an AF21 or AF22, AF23, or maybe a CS2 or a CS3. How do those map to DSCP values? And you might not have even known that they do, but they do map. So let me show you. I'm going to just draw the type of service byte here. The type of service byte consists of 8 bits. So here are those 8 bits here in a nutshell. And by the way, the discussion I'm showing you right now, I have it in a document on my Box account that is DSCP mappings. And you can download it if you want to. So the first 3 bits of your type of service byte in your IP header, if you've got 3 bits there, that means you've got a combination of 000, 001, 010, 011, 011, 100, 101, 110, and 111. And if you look at those from a decimal perspective, That's a value of 0, 1, 2, 3, 4, 5, 6, or 7. So this is your your class of service here for the first 3. Now, the next 2 bits here, the next 2 bits is going to be your drop probability. These 2 bits here are referred to as ECN bits. ECN bits are explicit congestion notification. So if you guys have been long enough to know about frame relay, remember beckons and beckons, explicit congestion notification, same thing is happening here. So this is if you're using ECN, it's not part of DSCP. And then this bit here is just simply not used. So if you happen to have an AF3 class of traffic, for example, the AF3 class would mean that you've got the first 3 bits set up as 0, 1, 1. This is your class, the AF3 class of traffic. So AF3 has 4 categories built into it. So those 4 categories are a CS3, an AF31, an AF32, and an AF33. So the second digit, the 1, 2, and the 3, corresponds to the drop probability. So if you've got 2 bits here, these 2 bits gives you 4 combinations. 0, 0, 0, 1, 1, 0, 1, 1. That equals a value of 0. This equals a value of 1. That equals a value of 2. This equals a value of 3. So for example, if we had a value of 1, 0 here, that would equate to a value of 2. So all of this collectively then would be an AF3 and a 2, which means an AF32. If this value here equals a 0, 1 instead, a 0, 1, then that will be equal to an AF31. Okay? So that's the bits in the type of service body. So let's see what this really does mean though. If we had an AF31, that means that these 2 bits here are set and we have a 0 and a 1. That's the bits that would be set in this type of service body. Now, DSCP equals a decimal value to begin with. So the way decimal values work, let me change my color to blue because it's getting messy here. This is DSCP. DSCP looks at the first 6 bits. So this becomes a value of 1, 2, 4, 8, 16, and 32. So all you've got to do is add the ones together. So 16 plus 8 equals 24, plus 2 equals 26. So a DSCP value of 26 means exactly the same thing as an AF31. They're one and the same. So when you say DSCP 26 and when you say AF31, it's exactly the same QoS marking. It's the same bit positions in the header. Now, the document, if that makes sense, great. If not, there's a document that I've provided for you guys, and it's out on my Box account. And I've got it also here as well in my handouts. If I can find it, it's called IP Presidents to DSCP Overview. So if I bring that over here, this is the document that you can compare. So if you open this up here, we use an AF32 as an example. So if we look at AF32, here's AF3 and here's 2. So if we highlight that, you can see that an AF32 is a 0, 1, 1, and then a 1 and a 0. That's going to be equal to a value of 28. If you had an AF31, that's going to be a value of 26, just like I said. If you've got a value of an AF43, an AF43 equals a DSCP value of 38. It's the same bit positions in the header. And at the very top of the column there, I've got it outlined for you. Here's the weight associated to each one of those bits. There. All you got to do is add the ones together. So hopefully this will make sense to you going forward. If you already have an understanding of QoS, I apologize for wasting your time. But usually understanding how AF markings map to DSCP markings, it's actually a pretty good bit of knowledge to have, to be honest with you. And then just like we did for the zone-based policies, in your localized policy, we create that policy and we need to be able to associate it then to our device template. So you go down to the bottom of the device template page, and then you will have a policy setting under additional templates, and that's where you will bind your QoS policy to. And once you've done that, it's for the most part done. Now, under ACLs and QoS, within your feature template, is where you can also define your queuing strategies, your policing strategies, and so on. So that is it. So that you guys allowed me to configure or to go through the lecture on all three of the modules. And so what you guys have left, and I know it's 5:30 right now, you only got, in essence, about an hour left maximum. We go, I think, between 6 and 6:30. But spend as much time as you can in your labs. Our goal today is for you guys, if you haven't finished up through lab 9, certainly that's the end of your policies. Lab 10 is just it's a show and tell type of a lab where you log into vManage and you log in your routers and you do your show commands. TLOC extensions is lab 11, and those are the only 2 labs to support the afternoon material. So if you don't get any labs done by the end of the day, I would jump directly into lab 11 first, and then come back and do the verification and troubleshooting commands second. So let's jump to the TLOC extensions lab. I want to show you this. So right now, your lab, you have your Site 10 and Site 20 router. So this guy's connecting both to Gold and also to, wow, they changed my configuration. Wow. Okay, I'm not quite sure if you follow this lab, I'm not quite sure if it's going to work the way that I wanted it to work. I hope they rewrote the lab so that they tested it. That's about all I got to say there. But they're having you guys first and foremost kill both of your network connections here on this router. And you've got connectivity from both of the routers' perspective only to the Gold transport. You have no transport connectivity on Site 20 at all. So if you set up TLOC extensions between these routers and then you log into Site 20, if you do a show OMP connect, show control connections, they should all be visible via the Gold transport. So if you see any at all, that will mean that the only way you could is across your TLOC extensions. Now, I have not seen this lab that they rewrote. I hope it works, but that's the intent behind the lab exercise. So let me kind of quickly go through here. That's pretty straightforward. They're having you create feature templates. You got to shut down the ones that's on branch VH2. You're configuring 2 sub interfaces, 020, 2 gateways. You're gonna, you know what? They're doing exactly the same lab that I had so far. And then on I hope they tested this. If you go through this lab, you guys, and it does not work as the lab says it